All right, guys. So let's go back to we're talking about delay, and we solved a few examples. So we did whoops, example 4.4 from the book, and then that example there was one inverter, kind of a minimum size inverter, driving um, M other inverters like itself. Okay. By the way, I'm going to start with, you'll see this in, circuit descriptions at the gate level. I'm going to say of it like a times one inverter is kind of equivalent to your basic, smallest inverter you can have. Okay, so if I draw an inverter with like times 10, you'll know that it's supposed to have a lot more drive. It's going to be bigger. So this guy will be 20 times the width of a smallest drawable PMOS, and this will be 10 times. Okay, so basically in the example 4.4, we had a small minimum size inverter driving M other minimum size inverters. And we ended up with an equation for the delay through this guy of RC times 3 plus 3M, where again, M was the number of inverters you were driving like yourself. Okay, and we called this, and this was kind of the delay for just driving your own parasitics. So we call this the parasitic, and this was all the loads you were driving. So this ended up being the load delay component. Okay, so that was example 4.4. And then example 4.5, we had an inverter that was W wide. So again, by that I mean that the P's are 2W and the N's are W. And that guy was driving M times 1 inverters. And the equation for that was M over W. Okay, and again, this was the parasitic, and this one was the load. Okay, so let's see if I draw this thing on as a function of, I don't know, I'll draw it as a function of M. And let's call this delay, or TPD, I should say. Just call it TPD, prop delay. Okay. So let's say this is 3RC and this is 6RC, and this is 9RC. Yep. Okay, and then M is the number of devices you're driving. So this M is how many of these guys are driving. And so it's a discrete number. So remember that, you can't drive like half of an inverter. So M will be like, be like 1 and 2 and whatever, 3. That's the number of things you're driving. So let's say if we plot, this guy in green, okay, when M is 0, that means you're not driving anybody else, you're just driving yourself. So at 0 means you're just sort of seeing the parasitics, you'll be here, 3 RC. And then when M is equal to 1, you'll be at 6 RC, and M is equal to 2, you'll be at 9 RC. So you'll be up here. So sort of as the number of devices, load devices you're driving increases, your delay through your gate driving them increases in that case. Okay. Now let's plot this guy in the same plot. Okay. Again, so this is like something that's like wider, W wider than the minimum size inverter. And so we said the parasitic delay ends up being the same because when you make the devices wider, the resistances goes down, but the capacitances, its own self-capacitances, go up by the same ratio. So when M is equal to 0, it is also down at 3 RC. At M equal to 1, it depends on the W. Okay, so let's say W is equal to 10, for example. So it's 10 times bigger than this guy. So then it'll be 3, so it'll be 1 over 10. So it'll be 3.3, right? So it'll be, so I don't know, like here somewhere. And the 2 will be, here somewhere, I don't know, something like that. So it'll be another line. So this is W is equal to 10. This is W is equal to 1. Okay. So something that's pretty obvious here, and we're going to make use of, is that the delay ends up being a linear function of the number of gates you're driving. Okay, so basically we can predict the delay as we add the number of delivered devices just by, we have a line. So that's good. So that's helpful. But, and then we want to, that'll become useful. But really what we want to do is, like we said, we're more interested, this is the delay through a single stage, but we almost never are not just looking at a single stage. We're looking at multiple stages. So for something to be useful, I'm just gonna, I drew this just sort of random thing. Let's say you have, an inverter and a 3-input NAND. This is random circuits driving a 2-input NAND, and it's got, it's driving so this is, times 3. It's driving a large inverter, and that's driving a 1 input of a NOR gate, and it's a times 2. And we want to figure out the delay through this guy. So the upshot is we want like a more general model of delay. So what do we do here? Because, and what are the different components? Well, so one thing is we're driving not just M identical gates, we're driving in a general case. Usually we're driving different types of gates. And, we're not like just an inverter driving something like ourselves. And I drew this really badly, but this was supposed to be a NOR, supposed to be an NAND. So a NAND is driving a NOR and an inverter. So we want to come up with something more general. And so that's where we come up with sort of this. Let me just erase. These are the previous notes I had. So let's look at this. So the first thing is, so again, we have delay. Okay. And notice that the delay, for whatever lucky reason, was always in terms of 3RC. Okay. Remember, R was resistance for a particular process, the nominal resistance of the equivalent resistance of a NMOS transistor, and that's typically given to you, although you could simulate it or calculate it, but it'll be a value. Like we said, in 65 nanometer process, it was 10 kilo ohm in our example, and C was 0.1 femtofarads for the same process. But this 3RC is like something we can basically have it ratioed out. So we're going to define a delay that's independent of 3RC just by dividing the absolute delay by this ratio. We're going to call it tau, okay, time constant. Okay, so it's basically like a relative delay. And then for each process, we plug in a different tau. So these delays, so anything, we basically, at the end of, as we'll see in the end of our examples, we just multiply everything by 3RC, and the RC is defined by the process you're in. Okay, so if we do that, our delay, this relative delay ends up being a linear function of two parameters. The first parameter is the parasitic. So let me write, let's take this guy, right, from our example 4.3. So if we call delay TPD over 3RC, we're going to end up with 1 plus M. Okay. And the 1 is the parasitic component, P. So this guy. And M is our component that we now are calling, this is our load component. Okay. And we're calling that effort delay. And then we're further defining this effort delay as a product of two components. One of them being what's called the logical effort, and the other one being called the electrical effort, or the fan out. Okay, so why are we doing this again? It's because we want to find a way to get a general result of any type of gate driving any other type of gate being loaded down by some other gates, okay? So we're gonna put everything in terms of equivalent capacitances, because all the gates, everything that's being driven looks like a capacitor. Okay, so for example, if we look at this logical effort, right? This is because, as I said, we have an inverter. and it has a certain drive. Now, if we said instead of an inverter, we want to have a NAND gate. Say, okay. So, let's see, who do I bother now? Stephen. He answered, he didn't give me a sound check, so I'm going to pull you into this. Stephen, can you help me out with this?
Hello?
Huh?
Oh, can you hear me?
Yeah, I can hear you, Stephen. So what I'd like to do is to size this NAND gate, this guy, to have the same drive, the same equivalent like current output or the same equivalent resistance as this inverter. Okay. So can you help me size these devices? So basically we want to make, let's say we want to make the pull down resistance, this pull down resistance, the same as this pull down resistance. What do you think we should make the size of these two devices?
Professor,
Sorry, I don't really know.
Okay, let's work on it together. So
Professor, can I say it be like a half be like a, is multiply 1, but we have to like a divide by 2. All resistance be like a half a.
that's correct, Jeffrey. Yep. It has to be resistance is half because let's Steve, is it Stephen or Steve?
Stephen.
Stephen. Thanks, Stephen. So here, do you remember what this guy's model looked like in NMOS? By the way, is it Jafar? The pronunciation?
Jafar.
Jafar. Yes.
Jeffrey.
Yeah. Great. Just wanted to make sure, Jafar. Thanks. So Stephen, Jafar is correct, but let's work it through here. So this like is NMOS times 1. Do you remember what the resistance, the equivalent resistance was? Or what the equivalent model was?
No.
Okay. So it was basically, a resistor. Whoops. Let me pull it down here. It was a resistor with a switch, and it had a capacitor on the drain and a capacitor on the source and a capacitor on the gate. And we said these are all the same, and this is like some resistance, some equivalent resistance for a process. Okay, so if I just look at the resistor component of this guy, all I see is this resistor R hooked up to ground. So it looks like that. Okay, with me, Stephen?
Okay.
So then now I have 2 devices in series, and I want, when they're in series, I want the resistance to equal to this. Okay, so basically I want, let's call this the resistance of this guy and the resistance of that guy. Okay, so I want R sub X plus R sub X is equal to R. I want this total resistance to be the same as this total resistance. So these two R resistances, R sub X, that we're trying to figure out, I want to set it equal to R. Okay? Okay. So basically I just end up with 2Rx is R, and R sub X is R over 2. Okay, so we'd like the resistance, as Jaffer said, we want the resistance of each of these to be half the resistance of this guy for this total resistance to be, okay, the same as the total resistance of that guy. So what kind of, how should I, if this is a size sort of times 1, what do you think I should make the size of this to make the resistance half of this? Remember, the size of the resistance just goes up with the width.
So half it?
Okay, so we want the resistance to be the half. So we want, remember, the resistance goes down the wider we make the device. So if we make the device half the size, its resistance is actually going to be twice as much. So really what we want to do is make the width of the device be a 2x. We want to get a 2 times wider device to get half the resistance. Does that make sense?
Yeah.
Okay. So basically you end up with 2 and 2 on the bottom for the N MOSFETs. Okay. So there's a little bit of more pain to go. Okay. So now for the pull-up, it was the same deal. Let me get a nice color here. And so this equivalent was just R sub, so it was the resistance of a minimum size PMOS was 2R. We had half of them, so it ends up being R. So basically, you will have an R going to VDD. And we want the sizes here to be the same as the resistors. Like if one of them turns on, we have the same resistance. What should we make these sizes?
Can I say it?
Nah, Jafar, give Stephen a chance. I want to torture Stephen as much as possible. So basically you want them to be the same, right? Because this is R and you want to make this R. So you just make it times 2 as well. Does that make sense, Stephen?
Can you explain that one more time?
Sure. So in a NAND gate, whoops. So in a NAND gate, either one of these devices could be on and still get a 1 value 1, right? Either you could have this on to get a high value, or you could have this one to get a high value, or you could get both of them on to get a high value. The sort of the worst case resistance is when only one of them is on. Okay, so when one of them is on only, you want the resistance of the same as being this guy, right? But this guy is also, so it just has to be this guy. Let's say this one guy has to have the same resistance as this guy. So you make it the same size. Did that make sense?
Mm-hmm.
Because you want a sort of a worst case one. So you make this guy, whoops, you make this guy times 2 and you make this guy times 2. So now this NAND gate will have the same, if you try to get a 0 out of it with these sizes, so you make the N MOSFETs twice as wide as these N MOSFET, the resistance, the pull down resistance is the same as the pull on resistance as our, nominal inverter. And the pull up resistance, if you just turn on one of these P MOSFETs, is the same as the pull up resistance of the nominal inverter. And so that's how we make it equal. Okay, so one more question. So this nominal inverter, like I mentioned, they have the gate of the NMOS has a capacitance of C. So, and then so does the gate of a PMOS. For a PMOS of one size, you have a capacitance of 1C, but we have two of them. So if I look at the gate capacitance, I'll get 2C of gate capacitance for the P and 1C of gate capacitance for the N, right? So if I look at one of the inputs here, what kind of gate capacitance would I get with these sizes? So I have a 2 wide P and a 2 wide N. So if we just look at the capacitance coming from this PMOS, what would it be? So we got 2C for this guy. So for this guy, it's the same size, right? So that'll also be 2C. And then what would be the capacitance of this N MOSFET? It's 1C here for a times 1, and we have a times 2.
Will it also be 2C?
It'll also be 2C. Thanks. Okay. So the total gate capacitance here is 3C. The total here is 4C.
4C.
Yeah. Okay. Thanks, Stephen. Thanks for being a good sport. I'll pick on somebody else now. So here's a case where you see that in NAND gate, for it to have the same drive capability, it'll have to have bigger devices. So it has higher load capacitance when other gates drive it. So this NAND gate, to have the same drive capability as a similar size inverter, will show a bigger load to these guys. So if you have a complex circuit, like a NAND gate, 3-input NAND gate will be even higher input capacitance, as we'll see as an example, than you guys did before. So we're putting this logical effort, which is sort of measuring the relative ability for a gate to deliver a current compared to an inverter having the same value. And it just ends up being the ratio of the gate capacitances. So you guys have to bear with me, this gets a little confusing. So if we say G is equal to 1 for an inverter whose gate capacitance is 3C, okay, the G will be, for a 2-input NAND gate, will be 4C over 3C. We calculated as 4C for a 2-input NAND gate, and the ratio between that and the gate of an inverter is 4C to 3C, or 4/3.
Professor?
Yeah.
Quick question. So the G is just then a ratio?
G is just a ratio of the gate capacitance of an input for whatever gate you have, the ratio of that capacitance to the gate capacitance of an inverter.
Okay.
Yeah, it's unitless. It's just a number. Everything we're talking about here is unitless, and at the end we multiply it by 3RC, which has units of time, and then you'll get a delay number.
Okay.
So, another way to look at this 4/3 number for a 2-input NAND gate is that a 2-input NAND gate has, like, just looking at its structure, the fact that it's got this sort of this series pull down for N MOSFETs, it'll have, just because of that structure, regardless of what size things it's driving, etc., just because of that structure, it'll have a 4/3 times higher delay than an inverter. Okay, so more complex circuits will have larger delays. And we're basically, by looking at the ratio of input gate capacitances to the input gate capacitance of an of a inverter, we call this logical effort to make up for that. Okay, this gets very confusing, but I just bear with me. Hear the story out, and we'll do some examples. Okay, so the next thing, and this one's a little bit simpler, is called the electrical effort. Okay, it's this guy down here. And this guy is just the ratio between what you're driving and your own input capacitance. So basically, the input, you're looking at the input the total input capacitance that you're driving compared to your own input capacitance. Because of the way we're sizing our logic gates, our input capacitance gives an indication of the drive that we have, right? So it tells us, that typically the higher the input capacitance that you have, the higher, the wider your device is. So you'll be able to have a smaller delay. But if you have what you're driving has higher input capacitance, then they're just harder to drive. The higher that capacitance is, it's just you have to charge and discharge it. But the input capacitance is an indication of how much drive you yourself have. And so that's the second definition, which is this electrical effort, which is the output capacitance that you're driving compared to the input capacitance of yourself. Okay, and this is called the electrical effort or fan out. So G times H together determine this load delay. So G times H, they call it the effort delay, basically the effort to drive other gates. Okay, so again, G is just a function of the complexity of the gate you have that's doing the driving. So for example, as you know, a 3-input NAND gate will have a higher G value than a 2-input NAND gate because it's more complex. You'll have to make the devices wider, so it'll sort of create a bigger load for its inputs, and it'll have a bigger delay. So its G number will be higher accordingly. And then just this value of H has to do with what kind of capacitance you're driving. Okay. And everything is like ratioed here. And then finally, this one is pretty simple, is the parasitic delay is just a delay that you have on your drain, on your output compared to the capacitance on the output of a unit inverter. So here, if you guys remember, there's 2C coming from the PMOS and 1C coming from the NMOS. So this is equivalent is 3C. So inverter P is 3C. I shouldn't say that. I just say inverter is 3C. Okay, and then if you look at this NAND gate, each one of these times twos has a 2C, 2C, and then this NMOS has its own 2C. So this is 6C on the drain. So NAND 2 is 6C. So the P is just that ratio. So P is 6C over 2C. Sorry, over 3C or 2. Okay, so let's do this. Let's do a oh, we already did the 2-input NAND gate. Okay, never mind. Fail. Okay, so basically ends up for an inverter, G is equal to 1, P is equal to 1, and D is 1. Remember, D is G, H, this is H, plus P. So D is equal to G1 times H plus P, which is 1. So just H plus 1. And here G we just calculated was 4/3 for the 2-input NAND gate. P was 2. So basically D ends up being 4/3 H plus 2. Okay, so what does this mean? Means that a inverter, this is the delay, so the less the better. So given a certain loading, an inverter has less delay than a 2-input NAND gate, and it just tells you by how much. And as the loading goes up, the NAND gate has a harder and harder time driving that loading than the inverter that always does better. Okay. Let's see. Okay, so let's do this. Let's do another example. So calculate the logical effort. So do the same stuff of 3-input NAND gate. Okay, why don't you guys give that a shot, and we'll do it together through that. right. Okay, guys, let's try this out. And this time I'm gonna grab Christian.
Hello, Professor.
Hi. You knew this was coming, didn't you, Christian?
I was hoping it wouldn't be me this time.
Okay.
So,
Let's give it a shot. So how would we size? Let's look at the N MOSFETs first.
right. So I was thinking the sizing would be, there'd be a 3x, right? The normal
Yep.
size. Is that correct? Okay.
That's
and then for the PMOS, it'd be still 2x, right? Since they're all
That's
in
right.
series or parallel.
Yep.
But I was trying to find a logical effort, and I was kind of confused on how to find the capacitance.
So
I think-
G.
Yeah, the G.
Yeah.
I think it's 2, but I'm not 100% sure about that when I calculated it.
Okay. Well, let's see the steps you would do. So you'd look at one input. Okay.
Okay.
And you start counting up capacitances. So this input for the P MOSFETs, what's the capacitance you'll have?
Would it be 2C, right?
Yep, it'll be 2C, this guy. And for the N MOSFET,
It'd be 1C.
remember you made this 3x.
Oh, right. So it'd be 3C then, right?
3C, yep. So in total, this guy is 5C. And then what was the inverter for the PMOS?
For the PMOS, it was 3C also, right?
Well,
Or total. Or
total it was 3C, yep. So PMOS it was 2, oops, sorry. So PMOS it was 2C, and the NMOS it was 1C. So total was 3C. So G is 5C divided by 3C, or 5/3.
Oh, okay.
We're almost there, but it's 5/3. Does that make sense?
Yeah, it makes a lot of sense. Thank you.
Okay, sure. Okay, so what's P? So
Parasitic delay.
yeah, so let's count up. So now you start counting up the capacitors at the output. Okay, so out here, what's the capacitance of each one of these P MOSFETs?
So there'd be 6 total, right?
6 total, yep. And how about for the NMOS? Now, NMOS, you're only going to see the top guy.
Top ones would be 3.
3, right. So this total guy is 9C. And then what's the total here?
It'd be
Or-
3.
Yep, 3C. So P is 9C over 3C is equal to 3. Okay. And so what's the total delay?
So this will just be the GH plus P, right?
Yep,
So it'd be 5/3 H plus 3.
you got it. 5/3.
So is H always just going to be like, we just leave it as H since we don't have the C out over C in?
Yeah, exactly. As you get the C out over C in, you'll plug it in, and you'll see where that will come. Yeah, because right now we're just sort of deriving, D versus H for like different gates. So you can see, for example, like a 3 NAND 3 is slower than a NAND 2. That's slower than an inverter. And you know kind of by how much.
Okay, yeah, that makes sense.
Okay. So I'm going to jump at, thanks, Christian. And in the end, we can do this for all of these logic gates, or we just do them for some, and you'll get a table like this this is the G's or the relative delays for different types of gates just based on their complexity. So G represents, the delay caused by the complexity. I mean, so does the P, but anyway, it's just one way to look at it. But so it's all referred back to an inverter, 1. So you can see like a NAND gate, and now and the interesting thing is how much worse a NOR gate is than a NAND gate. The reason for that is like a 2-input NOR gate Remember the G's we calculated from the input capacitance. The NAND gate, we just had to make this device, 2x this guy. And so we had a ratio of 4/3. Here, because of the NOR gate, we have to double the size of the P MOSFETs, and they were already too wide anyway. Now you end up with a CN of 5. So your G ends up being 5/3. So a NOR, 2-input NOR in a CMOS process is by nature, by architecture, slower than a 2-input NAND. And like you'll see that, like a lot of people, everything sort of breaks down into NANDs because NANDs are, if you can implement something with NANDs instead of NORs, it's more efficient. Okay. It's just the sort of the complexity comes from the P MOSFETs being slower than the N MOSFETs. So anyway, NORs are always less efficient than the NANDs for a given number of inputs. And then as the number of inputs grows, you also get less and less efficient. So this also tells you why. So you'll see a lot of NANDs anyway in CMOS. And then you won't see a lot of large number, like you won't see a lot of NANDs or NORs or any logical function that's more than 4 inputs because you're better off breaking those in terms of delay, breaking those into more sort of smaller input gates. It's just the delays to them get really bad. But anyway, you can, whenever you've got a circuit, so this is kind of the nice function of this logical effort, you can just look it up in a table and see what it is, okay? And same with the P's. So, they went through and calculated the equivalent P's for a ratio to a P of inverter 1. And then the interesting thing is the parasitic of the NOR isn't any worse than the NANDs. But then things get drastically bad with the number of inputs. Okay, parasitics get bad. Okay, so let's do another example. This is, by the way, guys, I'm just happy that some of you guys are on board here. This is like probably the most complicated thing to explain or understand in this class is this concept. And we're gonna go, unfortunately, we're going to have to go down a little bit more down the rabbit hole here. But anyway, just bear with me and just follow the steps. So here's another example. Once you guys take a few more minutes to work through this thing. So, but before you do that, let me describe what this thing is. So this is actually a circuit that a lot of people use to look at how fast a process is. So it's a it's a ring oscillator, so-called. So it's an odd number of inverters. Where the output of the last one is hooked up to the input of the first one. So why an odd number? If we look at this guy, we call this, I don't know, N0. This is N1, this is N2, and this is like N, or sorry, this would be N here. Okay, so if you look at that as a function of time, okay, so I'm just going to draw them on top of each other. So let's say this is, goes from the high to low, low to high, say, the N1, N0, and then N1, a gate delay later, N1, no, sorry, N1 is inverted. Okay, then, so this is like a delay later, then N2, a delay later, and so on and so forth. So after some amount of delay, then you'll get then this will be, you know, in N, okay, which coincidentally is connected to this guy. So basically it'll force this guy to, oh, sorry, NN is going to be doing this. So it'll force N1 to go back down. So basically it ends up being an oscillator. So you'll get, so something will happen here. Something will happen here. It'll take a long time, basically this number of delays, however many you have, to get to the output, but it'll have the opposite polarity because we have an odd number of inverters, and that will invert the input to what caused the issue. And so you'll just get an oscillation. So if you just leave the circuit alone, a little bit of noise here will eventually get this guy to oscillate. By eventually means very, very quickly, by the way. And so, and the interesting thing is you can use this oscillation frequency to measure the delay easily of these gates. Now, why wouldn't you, let's say you get your silicon back, okay, one thing you could do is to just hook up the input and output of your inverters to an oscilloscope and measure the delay, right? You could put in an input here and measure the delay going out there. Anybody want to guess why you wouldn't want to do that? Why that's hard to do? Remember we said that the delay through an inverter in like a 65 nanometer process was something like 15 picoseconds. So that's like a very, very short amount of time. And, you know, it was like, you know, 60 equivalent of 66 gigahertz. Yeah. If you invert it, like it's very hard to measure that with like, you know, your probes, even the most advanced scopes or probes, you got all sorts of capacitance stuff lying around. So you're not going to accurately measure a delay of 15 picoseconds. It'll be very, very hard to do, okay? But if you have a ring oscillator, this will be like oscillating, for example, in a 65 nanometer process, it might be, you know, oscillating at, you know, 1, 2, 3 gigahertz, something like that. And as you'll see, that oscillation frequency, because these are all the same type of device, it gives you, you can calculate back the delay of each individual inverter with a lot of accuracy. So you can use this to make sure your process is where you expect it to be. Okay. So anyway, you have this ring oscillator, which is N stages, all of them the same, all of them being inverters. So basically you guys are in this example are supposed to calculate, again, logical effort, electrical effort, parasitic delay, stage delay, and frequency. So this is G, this is H, this is P, and the stage delay is GH plus P. Okay, why don't you guys give that a shot real quick? Okay, guys, let's see if we can do this together. So this time I'll pull in Jafar. Jafar, can I get you your help in doing this?
Okay, sorry. It's
Sounds
a little
good,
bit
right?
hard, but
So what's the logical effort? So remember, this is just a logical. Each one of these is just an inverter.
yeah, is have it like a 3RC, but we have to multiply n.
Not just
Or-
all you have to do is go look at the table,
Mhm.
okay? And this was a table of G's, right, for an inverter. So you just have to read what the logical effort is. So the 3RC doesn't come in yet. Hold on to the 3RC, it'll come after we're done doing the calculations. But basically, logical effort is just one. Because remember, the inverter is the reference for the logical effort. So we said, the logical effort of a NAND gate, 2-input NAND gate, is 4/3 the logical effort of an inverter. So if you just have an inverter, the logical effort is just one. Then that's it. Okay? Does that make
Yeah.
sense, Stefan?
Yeah, but it doesn't matter. We have like a n stage. Is
Yeah, it
because-
doesn't matter. But for each one, see, right now we're just trying to find the logical effort of one of these guys. So maybe that's what I should have said. So we'll all this will come into, we'll add the delays to come up with the end stages. But right now we just need to find the delay through one of these, and then we'll multiply it by n to get the total delay. Does that make sense?
yeah.
Okay. So for each one of these stages, what's the electrical effort?
One right now.
Yep. Each inverter is driving just one more inverter like itself. So the input capacitance of the inverter is driving is going to be the same as its own input capacitance. So the electrical effort would just be one. Okay. How about the parasitic delay?
P. What was the formula of P? I forgot.
So you can just look it up in the catalog or the
Mhm.
table. And so the P is just going to be one also, because it's everything, the P and the G, they're all referencing to the inverter. So if you have an inverter, P is just also equal to one.
One.
Okay. So
Mhm.
here we end up with 1 times G times H
Yeah.
plus 1,
Plus one.
which is equals to 2.
Oh, H is one here. Yeah.
Yeah, because you're just driving
Mhm.
one other device.
Mhm.
That's exactly like you yourself. So just be 1. Okay. So now let's figure out so before we figure out the frequency, so now this is the delay. So we haven't talked about, we're not going to add 3RC yet. We're not looking at a specific process yet. So just think of it in terms of numbers. What's the total delay through here, through end stages? If the delay per stage is 2.
P. 2 multiply n.
Yep, exactly. So total delay is 2n, okay? But to get a frequency, because we need to go low, high to get the frequency. So when we're looking at the frequency, we're going to look at 1/2 times total delay, or 1/4.
Quarter.
Yeah. Okay. And now if we let's say we want to pick a process. So now let's say we want to do the 65 nanometer process. with R is equal to 10 K ohm and C is equal to 0.1 femtofarad. Okay. If we want to do that, then we figure out tau is equal to 3 times R times C. And in this case, it ends up being 3 picoseconds. Okay, so if you want to have the frequency for, let's say, n is equal to 31 stages and 65 nanometer process, we just do 1 over 4 times 31 times 3 picoseconds. And that equals to 2.5 gigahertz. Okay, so if you had a 31 stage ring oscillator in a 65 nanometer process that had this equivalent resistance and this equivalent capacitance, it would be oscillating at 2.5 gigahertz. It's fast, but you can still measure it. You might even be able to measure it at Cal Poly. I don't know what kind of scopes and stuff we have here. Okay. Okay, thanks, Jafar.
No problem. Thank you.
So let's do another example, okay? And this is
Professor,
yeah.
if I may interrupt you real quick. Where did we get the 2 for the frequency at the bottom? So it says 1 times or 1 over 2 times total delay. So where is that 2 coming from?
This extra 2?
Yeah.
Gotcha. So now remember, when we're talking about what happens is if you just look at N0, okay, which is at any point, it could be any point in this ring oscillator, right? But just look at N0 as a function of time. So it'll do something at this time. It'll go to 0, and then 31. So n, sorry, let me just do n. 2n times later, we'll get the opposite edge, right? It moves 2n times later. It's gonna move because each one of these is 2.
Yeah.
So n times later, it'll go to the edge changes, comes around the edge changes. Okay. Now remember though, the frequency. This is just half the frequency.
Oh, right.
You have to have another 2n before you really get the actual oscillating frequency. Does that make sense?
Yeah, that makes sense.
Okay.
Thank you, Professor.
Sure. Okay, guys, so let's give this a try. So now we got 1 inverter driving 4 identical inverters, okay? And we want logical effort, electrical effort, parasitic delay, and stage delay. So would you guys give that a shot? Okay, guys, let's see, this time I'm gonna pick the other Steve. We got Steve Polland. Steve, hi. Can you give me a hand?
Yeah. So I think for G, for logical effort, it'd just be 1, right? 'Cause it's
Yep.
still unit. And then for electrical effort, that's C out over C in, right?
I'm sorry?
For electrical effort, it's C out over C in.
C out over Cn. Yep.
So then would you consider C out just for one of the outputs of it?
No, you'd pick all of them.
So then it would be 12C over 3C, so it's just 4?
Just 4, exactly. And you can just think of it, I said these are identical to this one. So you just be 4, yeah. Or I think what you did was the safest bet because it's a more general way to look at it. And how about the parasitic?
So that's like internal, right?
Yep.
So would that be 4? Or
I mean, this is just, all you have to do is, this is the capacitance on the, so forget about these guys now. The parasitic is its own capacitance. And the ratio of that capacitance to the ratio of the capacitance on the output of an inverter. Well, it's already an inverter. So
just be 1?
it'll just be 1. Yep. Got it. And what's D then?
So that would be Gn plus P, so 4 plus 1, so 5?
4 plus 1 is equal to 5. Yep, you got it. Okay, now let's say, so now for the same 65 nanometer process that we had before, R was 10K ohm, C is equal to 0.1 femtofarad. And so we calculated tau already to be 3 picoseconds, right? This was 3 RC. So this is, if I want to get, like if I actually look at a delay, so the delay of 65 nanometer of this thing in 65 nanometer process, what would that be?
So that would be 5 times 3 RC.
Yeah, it'll be 5 times 3 RC or 5. So we already have 3 RC. So it would be 5 times 3 picoseconds or 15 picoseconds. Great. Thanks, Steve.
Yes.
Awesome. So, okay. So that's like examples of using this logical effort. And hopefully you guys start seeing like the benefits of it, because now we're kind of operating at the gate level in some sense. Okay, we're no longer, we use the transistor level, I don't know, the structures, and came up with these catalogs or tables for this G function, which measures the complexity of a gate, and P, which measures, it still measures the complexity of the gate, but basically different parts of it. And now we're operating at like a gate level type, like we're no longer looking at transistors, which is good, because if you're looking at like different levels of design hierarchy, you always want to be at the highest level of the design hierarchy that you can be, because you can always handle looking at more gates than you can look at transistors, and you can look at more logic blocks that you can look at the transistors and so on. So if you can move up the level of hierarchy, you can handle analyzing a bigger and bigger system. So we just stepped up looking at the delay one level of hierarchy. So we're just looking at gates. So that for the record, that was like a big win. Okay, so let me just start this thing. We won't go, this is where it starts getting kind of cool, because now, remember, we were doing all this as a prelude to figuring out how to optimize or calculate the delay of a multi-stage network. So let's say if you have this example. So you have you have a 10 times wide inverter, and you know you want this functionality for the sake of discussion. You just know at the output here, you know, you got to NOR this thing, then NAND it, then invert it. So you know that, but you don't know what sizes to make these guys. Okay, and you know eventually your load, whatever the next stage you're driving, is an equivalent of 20C of load capacitance. There's another gate sitting here that's got 20C of input capacitance equivalent. Okay, so basically that's what we're going to do going forward, is figuring out how to optimize this delay and how do we size these devices using this approach. And you know, the way we're going to go about doing it is because we can use the logical effort at the multi-stage network level. So for example, here, the total G, so we can also define a total G for this whole path, okay? It's gonna be a multiplication of the G's of the individual paths. So it'll be, you know, G1 times G2 times G3 times G4, or 1 times 5/3 times 4/3 times 1. Okay, because I know my functionality, I have all that stuff. So this ends up being, so I'll get 1 G, I don't know what that is, but what is that? 29ths for this whole stage, this whole multi-stage. Okay, and then the path effort, I can just do this output divided by this input. So it'll just be the output of the path will be 20, and the input will be 10. Okay, and the path effort basically ends up being those things. Basically, we can work through the path using the same structure. So we're going to go through that, but I just wanted to let you guys know where we're going, and I'll stop here and we'll pick this up on Tuesday. Any questions, guys? I know this is kind of like, again, pretty complicated stuff, and you just gotta sort of trust the math.
Professor, for that question with the 3-input NAND gate that we had earlier, they're talking about
This one?
the sizes of the transistors, you know, like the 2 and the 3.
Yeah.
How did you get those again? I think I missed something.
Sure. So basically, you want to get the total resistance here, the total pull down resistance, to be the same as the total pull down resistance here. Okay. Here, we just got one sort of a minimum size N. So its resistance is just R, right? So if we want to measure these, let's say I call the resistance here R sub X, because I don't know what I'm going to make those. So I have 3 R sub X is equal to R. If you're with me so far, Tim?
Oh, see, I do remember like you saying that the pull down resistance has to be the same. I was trying to figure it out because I was like, aren't they in series? But I guess.
Yeah, in the total of them in series has to be the same as the one. So the resistance of each one of those has to be 1/3 of the resistance of that one, so that when you put them in series, it'll give you a resistance of 1. And to make the resistance of each one 1/3 of the resistance of 1, you have to make them 3 times as wide.
Yeah. Okay. Yeah, that makes sense.
Okay. And then these guys are just, because they're in parallel, because we're talking about propagation delay is worst case when only one of them is on. And so just that's the same as this guy because they're in parallel.
Okay. Yeah, that makes sense.
Okay. Cool. Any other questions, guys?
Professor, I
Yeah.
had a question about something else. Were you able to post the solutions for the midterm?
No, I haven't yet. I'm sorry. I'll do that this weekend.
All right. Yeah. Thank you, Professor. I just want to, I'm still confused on number 2, so I just want to see how to do that one.
Okay.
Thank you,
Okay.
Professor.
Sure.
Oh, did we get our grades back?
Wait, no, I haven't. Sorry, guys.
Oh, okay.
I'm lagging. I'll get it out this weekend for sure.
All right, sure.
Promise.
Oh, I missed a day, so I don't know if you went over them. That's why I was like,
Yeah, I missed a day as well.
Sorry, I've missed quite a few days recently in my life.
it's a busy times. A lot
Yeah.
of stuff to do.
Yeah. We're trying to set up like a way for like, but I guess it won't work for you guys, but for Cadence to be available for next semester. So that's sucking up a little bit of time. But anyway, other stuff. Just excuses. Sorry, guys. I'm lagging. I'll get it out this weekend.
Professor, do you know if we're gonna have a VLSI lab next semester by any chance?
I don't know. I think Dr. Olson would be able to let you know.
That'd be
Next
cool if they could do like a simulation lab. That'd be pretty
Yeah, that's what we're trying to at least create the so what we're doing is, hopefully we're close to it. So we're putting together a entity that will put up a server outside in a co-location facility, so you guys can VPN in. And Cadence was nice enough to help out, and Cal Poly administration, I think, is nice enough to let us do that. So, like, you won't be stuck to being in the labs to access Cadence. That's why we don't have them this semester. So next semester, hopefully, if all that goes well, we'll have it set up that you'll have access to it. But I don't know if the school is going to be offering a lab or not.
Okay. It would just,
Next semester is virtual again. Is same as this semester.
Yeah, that's what I've heard. So we're trying to enable the Cadence tools so that people can still use them virtual, but I just don't know if they're going to be offering the VLSI lab or not.
Yes, some of the other labs weren't available either. Like the 3810 lab wasn't available.
Wait, next semester?
Yeah.
Really? What the heck?
Yeah. No, I checked. I keep looking every day.
That's weird. I have it this semester, and
yeah.
I mean, I could kind of understand because it's not like it's so hard to learn anything because like it's all like motors and induction motors and machines, and it's like, how do you supposed to?
I mean, it makes sense, but
yeah, it kind of does suck though.
Too bad it's going to push me back by another semester.
Dude, you should just try to get like a math minor or something if you're going to be there for an extra semester, and maybe you might as well just stay the extra year. Try to get like a minor or something. It sucks, but
I don't know. I just want to get out of here.
Yeah, don't we all?
I'm like short by 0.3 units, so I'm like, that's why I'm like trying to look for a lab. So if there was like a VLSI lab, I'll just take it and get it out of the way. Otherwise, I'll have to ask for forgiveness.
Oh yeah, and did anybody else not get an email for their registration date?
I didn't, but luckily I looked it up before, so I was like,
oh, I didn't. I was like two. I was like,
oh, they didn't.
I was like 2 days late, so I wasn't able to get a couple classes, but I was able to get. I was able to get some.
I swear it gets earlier every semester. Like,
and like, yeah,
it's halfway through the semester, and I'm registering for the next one. I'm like, okay.
You think of all semesters that this one where everything's online is the one where they'd be on top of sending people emails, but apparently not.
Honestly, we need a bigger department. That's our problem.
Yeah,
we have two
that's
people.
The thing. There's not enough. there's not enough professors for certain classes. Like, yeah.
Oh yeah, like half of the electives are not even in the next semester.
Yeah, yeah, seriously. I thought this was an engineering school.
Yeah, I think they've had trouble getting people to teach multiple sections because a lot of professors are. You see them. I remember Pagnon had to teach like 4 sections of the 3101
Yeah.
lab because no one else was doing it. I was like, what is going on? It's so crazy.
Yeah, no, it's like, yeah, in some classes it's like 1 section a semester, and that's it, and it's a required class. So
For one of the biggest majors in the school as well. Like I think we're probably one of the most impacted majors because I've never seen so many waitlisted classes in my life.
Yeah.
I'm surprised. I'm surprised I even got this far. Getting the classes that I did. Like I've barely been waitlisted in the past, but this semester I just got railroaded.
At the start of this semester, I was looking at all the senior design classes, EGR 48, 10, and 20. Like every department had seats open except ECE department, like all 48.
Yeah, I saw that too. Everything was open, and then you scroll down to the one where it's like ECE, and every single one is waitlisted. I'm just like, what? That's crazy.
See, guys, that's by purpose. Every electrical engineering department tries to create a siege mentality in the mind of electrical engineers that'll become very useful later in life.
It's more of a disappointment mentality for me because I don't have a choice. I have to wait to register. I'm just like, what am I supposed to?
Just remember, Tim, the whole world is against you.
I know that.
It'll be true every time.
Yeah.
Yep.
Yeah, ECE department taught me that pretty fast, pretty much year 2.
Yeah.
I was like, wow, you really gotta just get on 1,000 wait lists and just hope you get in, or just bug the professor until they let you in.
I have a bad news too. Margaret leaving too, and the EC department is shut down. I think so.
She's going on vacation, or she's like leaving?
Yeah.
Yeah, Margel's retiring. I think this
Oh my god.
I wouldn't even. I'm not even surprised. I'm not even
We
surprised.
completely shut down. I think so.
Dude, she was the only one like handling stuff.
Yeah.
And, like I emailed her, and I never got an email back for like 2 months. And then
Yeah.
I emailed her again, and then I got an email the next day. I was like, what? Like, I know she's busy. I don't get why we don't have more people. Like, it's so crazy.
More people managing that. Maybe that's why no emails for the registration thing went out.
That's probably why.
Yeah, most likely.
I don't know. If they don't do stuff about it, I think our schools. I have a feeling our school might fall off like a BET requirement or accredited schools, because I can't see it like staying up there on the engineering list if like we just have a lack of professors and stuff. It's lack of staff. I don't know.
Or maybe it'll turn into a badge of honor, like, oh, you actually managed to graduate from the school with an engineering degree.
Yeah,
that's an accomplishment.
I should put that on my resume. Managed to
yeah, there you go.
Graduate with.
I feel that way about UCSD, guys. I'm very proud to have survived. I didn't learn anything, but I survived, so that's good.
Yeah, it's kind of a trade-off between either you learn a lot and you get like an okay grade, or you get a good grade but you learn nothing. So it's like there's only a few classes where it's like you get best of both worlds on that, but most of it you have to teach yourself. That's what I've learned.
Yeah.
Or it's like 60% you, then 40% the class.
Yeah, something like that. Well, luckily the internet can shore up any. I mean, I don't even order the books anymore. I just use the internet.
Oh, I haven't bought a book in like 2 years. Like I don't even. It's not even worth it, honestly. Like I can literally search up problems from a textbook and find the problem without even buying the textbook. Like there's no point.
If we're talking about EC, there's always some Indian guy making YouTube videos.
Oh yeah.
Yeah.
The problem is understanding them. I'm just like, I don't know. Yeah, it's great.
Thank you, Professor. Have a nice weekend.
Okay, you too, guys. Just
Yeah, have
remember,
a
it's
good
the same. It's the same everywhere. It's just building
Yeah.
up the character.
All
Thank you,
right.
Professor.
Have a good one, Professor.
Thanks. Take care, guys.
Yeah.
Bye.